Alright, let's look at the homework 9.4, problem number 2. Alright, suppose that the population grows according to a logistic model with a carrying capacity 6,500 and a K equals 0.0017 per year. Alright, so we have to write the logistic equation. Alright, so let's do that. Alright, so K is 0.0017, then times P times 1 minus P over 6,500. Alright, so that's the equation. So let's type it in. Alright, so we have 0.0017. Alright, P times P 1 minus P over 6,500. Alright, so let's check the answer first. Alright, submit for testing. Alright, it came back and looks like we got part A correctly. Alright, then let's do part B. Draw a direction field. I'm going to use a GeoGebra to do that. So I'm going to bring up a GeoGebra. Alright, so here we need to do, I'm going to actually define capital F of x comma y. Alright, so this is going to be equal to, alright, so we have a 0.0017. Alright, instead of P, I'm going to use Y. Alright, then 1 minus Y over 6,500. Alright, so put that in there. Alright, let's see, 0Y. I guess you can't see it like maybe here. Alright, I have to fix that. Let's see. Oh, maybe here. Maybe because of the rounding. Let's see. I don't know. Yeah, it is. All right. Then I'm going to draw the slope field. So slope field. All right. So y prime is equal to f of x comma y, and then hit enter. All right. Let's see. Oh, actually, maybe just this might will do it. Alright, so slope field, and let's see, we have to change the scaling a bit. Alright, so 6,500 is, so I have to actually shrink this thing quite a bit. Alright, so 6,500, let's see, right, somewhere right like that maybe. Then I'm going to shrink this a bit. So let's see here. Right, yeah, starting to see something. Alright, like that. Alright, then we're gonna, let's see, put the population with the initial population 1,000, 2,000, 4,000, and 8,000. Alright, so let's do that. So we're gonna do solve ODE. Alright, so equation. So I'm gonna just put the y prime equals capital F of x comma y, and the point is going to be 0 comma 1,000. Alright, then hit enter. Alright, so there's a solution there. Alright, then I'm going to just copy this. Alright, copy, and then paste here. Alright, with 2,000. Alright, hit enter. And here's a solution. And here's another one. And 4,000. And put that in there. Alright, then 8,000. So here, 8,000. Alright, so those are the solution curves, and let's see if we can find this similar one. Alright, so let's see. Yeah, so let's say 6,500 around here, going up like that. So it's probably this one right here. Alright, then here, what does the direction field tell you about the solution curve? All the solution curves approach infinity. That's not true. All solution curves approach 30 to 50. I don't know where they got that number. And some of the solution curve approach 0. No, all of the solution curve approach is 6,500, and looks like it. Yep, so I'm gonna choose that. Right. Then, what can you say about the concavity of these curves? Right. So looks like it's a concave up in the beginning and a concave down, or concave down all the way, or concave up all the way. So let's see. Alright, so 1,000 and 2,000 appear to concave upward everywhere. That's not true. Curves appear to be concave upward first, then concave downward. So that looks good. And the P0 equals 4,000 appear to be concave downward everywhere. So that's good. And that curve appears to concave upward everywhere. So this is going to be it. Alright. So let's check the, actually, maybe let's do this one too. What is the significance of inflection points? All right, so inflection point is probably somewhere around there. That's where the slope is the steepest. So the population is growing the fastest. So inflection points where population grows the fastest. All right, so let's check the answer first. Alright, submit for testing. Alright, it came back and looks like we got the right picture and we got the right answer here. Grows the fastest. Alright, so we got all parts of part B correctly. Alright, so let's look at part C. Alright, program a calculator or computer to use Euler's method with step size h equals 1 to estimate top population after 50 years, okay? And if the initial population is 1,000, all right? So let's do that. All right, so I'm going to set h to be a 1. All right, so I'm gonna start from 0. Let's see. Oop. Did I put 0 there? 0. And then 1,000 here. Alright, so 1,000. Alright, so formula here is just going to be, so I'm going to type in a formula. Alright, so is equal to, take the value in A1 and plus H. Alright, then I'm going to copy this formula. Right, and I'm gonna drag it down to, so if we have to go to 50, so I'm gonna go to 51, right? Then right click and then paste. Right, so we got that. And then here, so we have to do the Euler's method. So we're gonna take, so I'm gonna type in a formula, right? Take the B1 value, right? Plus h times f of a1 comma b1, right? Then hit enter, right? Then copy this, and I'm gonna paste it all the way to 51 there, right? So paste, right? I'm gonna make this a little bit bigger so we can see the numbers. All right, so at 50, Euler's methods tells you that it's 1,074. All right, so let's type it in. All right, so so 1,074 was the value. All right, so let's check the answer first. All right, submit for testing. All right, it came back and looks like we got part C correctly. right? So let's look at part D. So initial population is 1,000, and write the formula for the population after t years, right? So let's do that. All right, so remember that solution P of t can be written as m over 1 plus a times e to the negative kt, and where a is m minus p0 over p0, right? So let's find the A here. So A, so carrying capacity is 6,500 minus P0 is 1,000. That's the initial population, and divide by 1,000, right? So which means that you're going to have 5,500 divide by 1,000. All right, so we can knock off 2 zeros, right, and divide by 5, so it's going to be 11 over 2, right? And so this is going to be, so P of t, so I'm going to go down here, right, so we still have 6,500 over 1 plus, all right, so 11 over 2 e to the negative 0.0017 t, right? And we can probably leave it like that. Maybe I'm going to just multiply top and bottom by 2 so that I don't have a fraction inside a fraction. So you have a t plus 11 e to the negative 0.0017 t. And then numerator, it's going to be 13,000. All right, so let's type it in. All right, so we have, let's see, P is equal to, P of t is equal to 13,000 divided by 2 plus 11 e to the negative 0.0017 t. All right, so let's check the answer. Submit for testing. All right, for some reason they didn't like that answer. Maybe I shouldn't put the of t, so let's double check there, and hopefully it'll be accepted. All right, I came back and looks like we got this one correctly. So I shouldn't have put P of t. All right, so it's just going to be P. All right, so use this to find the population after 50 years and compare with your estimate in part C. All right, so let's do that. All right, so I'm going to actually just use the function, and here it's actually f of x is there, so I'm going to just find f of 50. It came out to be, okay, we want to get the decimal value here, right? So actually, so what do I need to do? All right, so one thing we can do is we can do numeric, and expression is f of 50 here. Right, which is about 1,074. All right, so let's go back, and 1,074. All right, so let's check the answer. All right, submit for testing. All right, actually I didn't read the question. Round 1 decimal place. All right, so it's going to be 0.1. All All right. So 0.1. All right. So let's check the answer. All right, so we got this one correctly. Then part E is just the, we want to look at the picture. All right, we've already done that. All right, so 1000, this is the one. So it's concave up in the beginning and a concave down. All right, so let's see if we can find it. All right, concave up in the beginning and a concave down. And let's see, which one is that? So a 6500 is going to be the equilibrium solution. So this last one is going to be the correct picture. All right, so one last check. Submit for testing. All right, it came back and looks like we got this one correctly. All right, that's it. I hope that this was clear.